Okay, so we were in the middle of talking about the analytical formula for barrier, right? And look back options. So this is like the, I like to call it like more like the expectation approach, right? By expectation, I mean, you take expectation, right? And it's to distinguish, right? This is the approach that is to be distinguished with, let's say, the PD approach, right? Or the Monte Carlo simulation approach. So this is like, if you want, right? This is the exact approach. There's nothing approximate about it, right? The other two, whether you use a PD or use Monte Carlo simulation, you always approximate something. And therefore, right, how well you can approximate things is the issue. Here, right, of course, the challenge is, can you even do the math, right? But if you can do the math, then of course, right, the analytical approach is always preferred because, right, is precise. So, right, but in real life applications, right, we don't really always hope for such a thing. But when there is something like this, right, we would like to understand the reason behind, right, and see how far we can expand, right, this apply this kind of technique. So what's the idea, right? The idea is, we talk about both of these, all right, and the reason is this: in both, right, in both of the barrier and a look back, and by barrier, right, I mean up and out, right, and up and in, I guess. The down part, right, will kind of be similar, but you have to kind of switch sign. So in both options, right, we'll have to deal with, right, so in both options, we need to look at the event, something like this. Right? Because, I mean, this is exactly the idea of being, right, knocked out in the, sorry, yeah. I mean, either K or L, right? We'll look at that later, but, some number here, right? If it's L, then it's going to be the event that the option, right, is out of the money in the barrier option, up and out. In terms of the look back, right, the look back call, this will be this subtract K plus, right? If if it's only this guy, then you can also think of it as like minus 0 plus or whatever, right? Either way, right? This is something that we need to look at. Also, right, from the point of view of what we'll look at later, but this is like related to the CDF, right? Cumulative distribution function of a random variable. But so as I said before, right? I mean, if you look at this, you'll see that it's something like this. Exponential of, right, r minus 1/2 sigma squared t plus sigma w, right? It's really w tilde t because we are looking at, right, risk neutral probability, right? It's like this. And we can move the max, right, first inside the S0 because it's positive. And then we can move it inside exponential because exponential is increasing. So it will be this and then max, right? Oh, sorry. This is little t because you take the max over all little t, right? Like this, right? Max over all little t, all right? This kind of little t. And then you take this max. Okay. And here we stop, right? The reason is, right, if we want to move the max inside the sum, both of these has to be increasing, right? Like we said last time. Now, this function is increasing if, right, this is positive. So that's, whatever, right? It could be, this could be negative if sigma is large enough. But the point is, right, you have no hope for the Brownian motion to be increasing, so forget about that. So anyway, right, there will be something to do here, and that something is to convert, right, this whole expression into a Brownian motion under another change of measure. We'll look at that later. But anyway, so under some extra, right, change of measure, it will become a W hat, all right? We'll take a look at that step, all right? But the point is, right, all in all, so, right, so some change of measure. And then, right, you see that, well, you can divide by S0, right? Take the log, divide by sigma. Then you get this, let's say bigger than some number, right? This number M is, divide by S0, take the log, divide by sigma, whatever. Point being though, right, that this very relevant event, right, whether it's K or L, doesn't matter, in both, right, Barry and look back, can be simplified down to this, which I'm trying to tell you is, right, right, because we will have to do something like this, right, expectation, or we have to do probability, right? So either way, to work with this expression, we need to understand basically, right, the distribution of the running max of the Brownian motion. All right. Now, of course, right, once you change measure, then this is just a Brownian motion under some further measure. So we'll drop the hat for now, right? We'll just look at some generic Brownian motion. So you have seen this notation before, right? We define MT to be the running max, right? MT will be the running max up to time t of a Brownian motion. All right. Now here, right, the expression is like this, but it's the same thing. And usually the CDF, right, is phrased more naturally under something like this. But like again, right, we don't really care if you know one expression, you know the other. So it doesn't really matter, right? One of these. All right. So that's the question, right? That's the question of the distribution of the running max, right? Now, here, right? So this is what I was referring to when I was saying, when you want to do the analytical approach, right? You need to work out the math, right? This is exactly the math that you want to work out, and maybe beyond it. And I want to pause a little bit here and have you appreciate, all right, how hard this question can be. Is if you have no experience on this, even if you have some experience, unless you know what the approach is, this is super hard. Why is that so? The reason, right, is because what is this random variable? Well, it's perfectly well defined, right? It's the max of a bunch of Brownian motion. But how do you understand this max, right? Is uncountable max of a bunch of correlated normal random variable. All right. What does that even mean, right? How do you even plug that in here and work out something using the normal distribution? That's unthinkable, right? From that point of view, right? Using the direct definition, okay? Using the direct definition of the running max to work out this expression is, as far as I know, is unthinkable, right? Because if these are independent normal, maybe you have some hope, I don't know. But these are correlated normals, right? The Brownian motions is correlated among themselves. Also, this is uncountable max. That's really right. Yep. So anyway, right? So take a moment, right, to appreciate how hard this question is. Yet, right, it's exactly what you need to figure out to work out this expression. Okay. So therefore, right, the following thing will be exactly why we want to look at, the next one, which is the so-called reflection principle. Okay. Now, the reflection principle is quite famous, and it's famous exactly because it allows one to deal with something like this. So we will discuss the reflection principle related to Brownian motion, but the same thing can be applied to reflection principle applied to random walk, all right, symmetric random walk. So you can see that also when people study, random walk, like a discrete stochastic process, right, which is exactly related to like the binomial model, for example. Anyway, right, what is the reflection principle? First of all, right, we need to tell you something called, there are two concepts here, right? The first concept is the concept of a reflective Brownian motion. And then, right, the second principle is exactly the reflection principle itself. All right, so we will talk about both of these. So first, right, let's draw a picture. So suppose we have a level M, all right, like this. So Brownian motion, right, always starts 0, right? It does what it does. Now, it's really a fascinating fact that, again, right, we're not in a stochastic analysis class, but there's one fact that doesn't matter how high M is, the Brownian motion will cross M at one point, all right? It will cross M at one point. That's a fact. But anyway, right, we're not concerned with that. But anyway, right, it will cross M at one point, and then it will continue, right, to do its business, whatever it does. All right, so of course, right, you know that so this is T, right, and this is, let's say, WT, right? So you know, right, that exactly this time right here, right, has a very special meaning for us. That's exactly something we call, right, a stopping time. Tau will be the first time, right, that the Brownian motion get over, right, the level M. Okay. Now, so this is just good old Brownian motion and a stopping time, right? We're used to this. Except before, I think we say this is the stopping time for the stock, right? So the stock is like the Brownian motion, but it starts somewhere above, right? It starts at 0, but the picture looks quite similar. But that's not what we're concerned ourselves with here. What we're concerned ourselves with is, right, at this moment, let me use a different color. What we'll do is we will, right, reflect the path, right? And I guess my picture will not be perfect, but something like this, all right? So what happens is, so we call this BT, all right? So what happens is this, all right? We have in mind two paths, all right? One path is the good old WT itself. Another path is like WT, all right, up to time tau. So it follows whatever it does, right? The red path is exactly like this, okay, up to time tau. But at tau, where WT, right, goes what it does, this red path will reflect, right, WT across the level M. All right. So that's exactly, so we refer to BT, right? B now for Brownian, right? W for Wiener, doesn't matter. But BT, the red path is exactly what we mean a reflected, right? And of course, the whole point is it's going to be a Brownian motion, but let's write down, right? Definition of a reflected path, right? So it will be, right? This will be very important, right? So there are a lot of concepts to take in here for today's lecture, so pay attention. It will be the same, all right, as the original WT path up to that first time, all right? However, right, after that, it will be reflected, right? How do we capture reflection, right? Well, you think about it, right? Reflection means that, right? So here, like this. So you start at level M, right? If you want to get back the Brownian motion, then you add, right? So this is WT, right? WT is, right? This is a truism, but what it means is that you start at level M and you add the difference, right, between Brownian motion and M, then you get Brownian motion. But of course, right, we are not adding, you see, we're not adding the difference, we are reflecting. So it's quite easy to see that BT then is this, right, start at this level, but instead of adding, we subtracting. You understand? So it will be 2M minus WT, right? But this only after that time. Are we clear on this? Okay. All right. So this is just right now we're defining a path, right? And exactly is writing down in symbol what I was drawing, right, in red in this picture. Now, so obviously, right, now once I write this down, then it doesn't matter, right, how the Brownian motion path looks like, there was always a corresponding reflected path. All right. The next thing, right, is exactly, well, what is the nature of this path, right? What is the nature of BT as a stochastic process, right? Because you define it, it's very, very well defined, right? So you can ask, well, you know, what is it? It is certainly a stochastic process, but can we classify it? And again, right, all the hints kind of point to something obvious already. But right, I want you to not, you know, get too much into the obvious thing and take a step back and appreciate, right, all the reasoning. So here you go, right? Here's something that might be intuitive like this. So suppose that you're well trained, right, looking at Brownian motion a lot, right? So if someone present you with a picture of WT, right, you'd be like, yeah, that looks like a typical Brownian motion path, right? Okay. Now imagine, on the other hand, someone presents you with a picture of BT, right? Without showing you WT, of course, right? You just present it with BT by itself, right? WT is hidden. Then just try to think about it. You would also, and no level M, right? You just saw the picture of the BT itself. You yourself would also say, well, yeah, that also looks like a Brownian motion path, doesn't it? Right? There's qualitatively nothing that would distinguish BT from a typical Brownian motion path. All right, think about it. This reflection right here might seem a little bit strange because we are doing reflection artificially. But if I take away all the tools, and if I ask you to only look at the red path, you yourself, right, will be very convinced that that's just a typical Brownian motion path. And in fact, right, this intuition of like looking is true, right? Is real, that BT is a Brownian motion. All right. So therefore, right, of course, in compactly, right, we just call BT a reflective Brownian motion. But right, it's very crucial that first of all, we defined, right, BT like this, and then we claim it's a Brownian motion. All right. Now, so of course, right, the question is why? Okay. Again, right, the intuition, I was telling you that if you just look at it, it looks like a typical Brownian motion path. Now, on the other hand, right, if you try to wave hand, you could get to something, but it's a little bit iffy. First of all, right, there is an idea I hope that you learned from Math Finance 1 called a stopped process. Have you heard of that before? So for example, right, if you have tau as a stopping time, right, whatever, doesn't matter. then you can do this, T minimum tau. Right? Have you heard of this before? So it's really simple, right? And it's not really important here, but so by the way, right? This notation, the wedge, right, is the minimum, right, between A and B. Okay, so that's what it means. So what does it do, right? What does the stop process do? It's very simple, right? So suppose you have a Brownian motion, right? It does what it does. Now here's tau is the stopping time, right? So this is WT. A stop process does what? A stop process, right? If T is less than tau, then it's exactly WT, right? If T is less than tau, then because it's the minimum, then WT minimum tau is WT. But if T is bigger than tau, then it's just W tau, right? If T is bigger than tau, then because the minimum, then it's just W tau. So what happens is, right, the stop process will be like this, right? Notice it's kind of similar to the other one, but right. So you understand, right? It stopped at the time tau. So of course, right, it's defined for T bigger than tau, but it's just a straight line because it stopped right at that time. Understand? Okay. So well, I bring up this process for some reason and you see. But basically, right, first of all, there are some relevance here like this, right? In martingale theory, a stopped martingale is a martingale. It has some relevance actually in American option, right? So the reason is this. You think about it like this, right? This theory is connected to like optimal stopping. When you think about gambling, right? Suppose you're betting on this process, WT, on how it moves, right? You're betting on a stock. Suppose that you say that, okay, besides like the usual investment, right? My portfolio choosing, I also include a time where I will judiciously exit the market or something, right? Because after that, you don't do anything else. After a certain time, I will exit the market. And of course, that time is a random time, right? It's not a fixed, like 1 year from now, I will stop. But maybe you say, after the stock hits, I don't know, a 500 level, then I will quit. Anyway, right, this theory tells you that even if you throw in a judicious stopping time, as long as, you know, it's a stopping time, meaning that you cannot look into the future to choose your exit, then you cannot win against the market if you bet on a martingale, right? So you cannot win against a martingale if your stop strategy, your exit strategy does not allow you to look into the future. So that's the relevance, and that will be you know, something that will show up in American option, right? In American option, you cannot beat the, you know, the option price by choosing a strategy that, you know, somehow exercise optimally as long as you don't look into the future. Anyway, the point being is I was trying to tell you, right, back to this reflective Brownian motion business, that BT, right, looks like a stopped Brownian motion, at least up to this time, right? So at least up to the optional time, the stopping time tau, it's believable, right, that this is a Brownian motion, right? At least up to this time, it's believable that it's a Brownian motion because, you know, it's exactly WT, right? After this though, right, it looks strange, but, you know, this is a constant, right? And this is a subtraction. Now, negative Brownian motion is still Brownian motion, right? Because Brownian motion is symmetric. So somehow you could also believe that, well, you know, it looks like Brownian motion before time tau. It looks like a Brownian motion lifted after time tau. So, you know, who knows, looks okay, right? But that's really waving hand, and that's not a rigorous way to look at things, exactly because, right, how does the two parts get connected, right? It's not simply that you just somehow divide the time flow like this and look at the before and look at the after, right? You have to somehow look at this as a single process, all right? So the Y here, right, is actually also a non-trivial, right, exercise in stochastic process. But let me tell you, right? Anyway, so to explain the Y, we need something called the Levy characterization of Brownian motion. So again, this is a highly technical stuff, right? But we want to explain everything a little bit rigorously. So do remember, right, that up to now we have two ways to characterize a Brownian motion. The first way, right, is by definition. So good old definition, right? But the definition is very hard to check. I mean, not very hard to check, but it's rather cumbersome to check, right? The second was the one we use in change of measure. In other words, right, the exponential, right, of theta, right, Wt minus 1/2 theta squared t, right, is a martingale. So this is called the martingale characterization, right? And of course, right, now with the Levy characterization, that will be the third way. Levy characterization is this. It requires two things. That Wt itself is a Brownian motion. Oh, sorry, that's silly, right? Because our motion is, of course, our Wt itself is a martingale, all right? It's a martingale. And second of all, is quadratic variation is T, all right? So if both of these are satisfied, then Wt is also a Brownian motion. So it gives us a third way, all right, a third way to characterize a Brownian motion, right, on top of these two. On the other hand, right, so now we want to ask, why is this true, right? Why is this true? Why does Levy characterization work, right? It seems okay, right? And by the way, it's actually like this. It's interesting to tells you, it tells you that Brownian motion is exactly the only martingale that has quadratic variation equal to t, all right, to t itself. So a martingale in some way is quite uniquely characterized by its quadratic variation in some way, right? Not totally, but. Now, why is that true? Why actually, it's actually just another way to look at number two, all right? In this way. Suppose, right, suppose 3 is true. All right, then you want to, right, we have show why 2 is true already. So now let's try to prove that if 3 is true, then 2 is true, right? We try to show that 2 holds, right? Why is that true? Well, to show that 2 holds, we can just go ahead and apply Ito's formula. Right, to show something is a martingale, you just have to apply Ito's and check that it only have martingale part. So D, right, of this guy is what, right? So let me call this something, right? Let's call it MT. So first of all, right, differentiate with respect to Wt, right, gives us, sorry, differentiate with respect to T, right, gives us minus 1/2, right, theta square MT dt, right? Differentiate with respect to Wt gives us theta, right, the MT dWt. And differentiate with Wt again, right? The second derivative is 1/2 MT, right? And then now, sorry, 1/2 theta square, right? MT, and now D quadratic variation of W. All right. keep in mind that, right, we don't know what W is, right? We don't know what W is, right? But Ito's formula, right, applies to generic, right, stochastic process. So as long as WT is an Ito process, we can apply this, right? Now, right, so this generically holds, okay? This generically holds. So now I will use, right, the three part. Part B, right, tells me that this is just dt. In other words, these two cancel, right, for using the quadratic variation hypothesis. Part A tells me that this is a martingale. All right, and that's it, because, right, D of this process is a martingale, which is exactly what we want. All right, so Levy characterization implies a two holds. Any question? Okay. So now, right. Let me try to think. Yeah. So now, right, we will want to apply the Levy characterization, right? We want to apply the Levy characterization, right, to BT itself, right? We want to apply the Levy characterization to BT itself. In other words, we want to show that BT itself is a martingale and BT has quadratic variation T. All right. We want to show that BT is a martingale and the quadratic variation of BT is T. Now, how can we do this, right? How can we do this where BT itself is something that looks crazy like this? So we want to show, right? We show Levy characterization holds, right, for BT. And how we can do this is by expressing BT as some stochastic integral dWt. All right. Now this is a very neat trick in this way. Sorry. So if I do this, I should write dWs, right? So in other words, right, I claim that there is a clever way for me to express BT as this. Now, why is this true? Why is this good, right? Why is it a very perfect way to work out a Levy characterization? For two things, right? If you have something like this, then the first part is obvious, right? Because an integral against a prime motion, an integral against a martingale is a martingale. So the first part is obvious, right? If we somehow we can do this. Now, what about the second part? The second part is this. The second part is if you look at the quadratic variation, right, of an Ito integral, remember, what is it? It's going to be just whatever this is, square ds. All right. And so this form will also allows us to look at the quadratic variation, right? And hopefully somehow this comes out to be T. Yes. So if we can work out whatever that is, yes, then we can check Levy characterization on BT. Okay, so far? So now, right, Now let's go back to what BT is. So BT, right, is WT up to time tau, and it's like this after time tau. How in the world that you can pull these two together into one single integral, right? Does anyone see how that could work? Right? So basically, BT seems like a piecewise definition, right? Which it is. It's a piecewise definition, but somehow you want to pull it into one single integral, right? Let me tell you, here's a clue, right? And if you have not worked in this business, maybe it's hard for you to see. But first of all, right? So I'll rewrite BT, right? So BT is WT, right? If T less than tau. But let me also rewrite like this, WT minimum tau, right? There's no harm here, right? Because that's true. If T is less than tau, it's exactly WT. Now for T bigger than tau, what is it? It's going to be reflected, right? So again, let me write down the reflection for you. So you see that it's not too strange, right? This is reflection, right? From the level M, instead of adding the differential, right? The difference, you subtract the difference. Anyway, right? So that's exactly 2M minus WT. However, right? I could also write it as WT minimum tau twice minus WT. Okay. Now, why in the world would I do this? Why in the world I would do this is because, right, M, remember, right, M is a level that you crossed, right? M is a level that you crossed, yes? And remember the stop process, right? After that stopping time, it will just level out. So therefore, right, this is exactly M right here. If you look at tau as the first time you cross M. So therefore, right, after tau, if T is bigger than tau, this is frozen at M. So that's just a fancy way to write 2M, right? It's a fancy way to write 2M. Agree? Now, but then, right, okay, so why in the world do I want to do it in a fancy way rather than just 2M? Here's a reason. Here's a reason is if you're in this business for a while, you will know that there is a very convenient way to write a stop process as an integral. Now, I want you to stare at this for 5 seconds or so and convince yourself that this makes perfect sense. All right, notice that again, right? I know this is not easy, especially it's the first time you see it, but it's very important you get all the details. This is not that trivial, right? I mean, it's trivial, but there are 3 times going on. 3 times going on, right? 3 times. First is little t, which is a deterministic time. Then there's tau, which is a stopping time. And there's the s, which is like a running, right, integration up to time little t. Okay, so there are 3 pieces going on. And it must be like this, all right? So why is this true? Think about it, right? Why? Because, right, why is this true? Because if t is less than tau, right, if t is less than tau, then of course you want the left-hand side to be WT, right? Now, what about the right-hand side? If t is less than tau, right, then s is less than tau, right? S is supposed to be less than tau. So you will never, right, and s is also less than t, right? here, let me show you. So the S is definitely less than t, right? Because you integrate up to time t. But if t is less than tau, then S less than t, it must be clearly less than tau. Yes. In other words, this indicator is always 1. Yes. Understand? So the integral S less than tau, dws is just the integral of 1, which is wt. You understand? Right. So basically, if you are at, if you are less than tau, then you just take 1, right? So you just integrate up to that. On the other hand, right, if t is bigger than tau, what happens? If t is bigger than tau, right, then this better be w tau on the left. How about on the right, right? On the right, you can do this. Because t is bigger than tau, right, you can do this. Agree? Because t is bigger than tau, you can split the integral from 0 to tau and then from tau to t. Now, of course, this is going to be w tau, right? On the other hand, here, right, because S is bigger than tau, right, that's what you're looking at, then this indicator function will be 0. Therefore, it's just leave you with w tau. Got it? So it's a nifty trick, right? But that's exactly also, this is, guess what? This is the reason why. What does it explain? It explains a fact that we mentioned earlier today in lecture. What does it explain? It explains that a stopped martingale is a martingale, right? Because actually this relation doesn't rely on right, whatever w is, right? All my analysis down here was just, right, checking the time. So this is true for any process. So in particular, if w is a martingale, then the stop process can be written as an integral against a martingale. Therefore, it must be a martingale. Understand? Question? Okay, so to test your understanding, right, let's ask you this. Remember, right, the whole deal is we want to show somehow BT, right, is something like this, right, by applying Levy capitalization. So we will get to BT later, right? But doesn't this form give you some thoughts? That seems like, right? Does that implies that a stop by motion is a by motion? Well, why does this seem like it could hold? First of all, right, this is a martingale, right? As we explained, because this is a motion is a martingale. What about quadratic variation? Quadratic variation, right, as I explained, was the integrand square, right, ds. Right now, the indicator function, right, square is equal to 1, right? So that's just also t, right? So a stop by motion is a by motion, isn't it? You understand? I was applying Levy characterization, right? It's clearly a martingale because it's an integral against a martingale. And if I take the quadratic variation, right, it's going to be this square, right, ds. Now the indicator square is 1, so I get t, right? So a stop Brownian motion is a Brownian motion. Yes, no, maybe.
Can I ask
Well,
a
let's take a look
question?
at the picture, right? Do I hear something?
Yeah, can I ask a quick question? So
You asked
I'm
me
kind
to
of
repeat the
confused.
question, please? Is that what you're saying?
Can I ask a question? So I'm kind of confused
Can you
because
ask the question? Yes, of course.
it seems like the quadratic variation, like when t is greater than tau, would be just tau, not t.
Exactly. I was cheating. Absolutely. Yeah, that's exactly the key, right? This guy will be 0 after tau. Absolutely. So therefore, it's not always 1. So it doesn't hold that the quadratic variation will be always t. Absolutely. That's exactly the point, Kareem. So that's not true. All right, that's not true, right? Yes. So you pointed out, right? If t is bigger than tau, right? Exactly whatever by the same analysis that we did here, right? This process after tau will be 0. So therefore, the quadratic variation will be stopped at tau. So that's actually not true, right? That's how you understand it. Exactly. Right. Actually, if you look at the picture, right, the picture also confirms. Does the red path look like a Brownian motion? Right. Obviously not, because a Brownian motion has to be nowhere differentiable. Right. A straight line is a horizontal line is very, very differentiable, right? So exactly, you see that BT, this is why, right? You cannot just stop after this time. You got to reflect it to get some interesting action out of it. Okay, understand now? But anyway, right? So that's kind of just to kind of, test your understanding, right? So now, having given you that clue, can you see how you can combine, right, these two pieces together with what I give you as some integral dWs? What is this mysterious business? Anyone? No, no one. It's easier than it seems. It's kind of staring at you in a way. Last chance. No taker? All right. It'll be this. You think about it, right? So I hope it's clear that it's this, right, after t bigger than tau. But why is it this when t is less than tau? Because if t is less than tau, this will just be 1. So 2 minus 1 is 1. Do you understand now? So actually, it's just this guy, right? All right. Any questions so far? Now, let us check the Levy characterization, right? It's clear it's a martingale, right? I don't have to do that. What about the quadratic variation, right? As Kareem, right, very well pointed out, right? You do something cheating like this, is not always t, right? Is this always t, the quadratic variation? You can do it like this, right? Before tau, then the integrand is 1, right? So the square is 1. After tau, what's the integrand?
-1.
Huh?
-1.
Correct, right? -1. So that's the key, right? You square, you still get 1. Therefore, it's checked. Are we okay here? Any question? All right, so that covers, right, the first part, the concept, right, of reflected Brownian motion, and why, right, you know, this red path here is a Brownian motion. So now, right, we didn't just cook up this guy for fun, right? Even though actually it is fun, right? It's a very fun analysis, right? Exercise in stochastic analysis and understanding, right? By the way, this something like this can also be done, right, for a symmetric random walk, as I said, right? But we will use this, right, in some way, right? We'll use this BT in a way. That's the reflection principle. And the reflection principle, right, let me tell you, is this. The reflection principle is just an equality. It says that these two events are the same. That for k less than m, right, these are two numbers. The event that Wt is less than k and Mt bigger than m is equal to the event that Bt is bigger than 2k minus m. Hold on. It is 2m minus k. Not 2k minus m. See? All right. So, by the way, right, this Mt is the running max, right? As we talked about before. So first, right, let's talk about why this is useful and what is this saying, right? First of all, I hope you don't feel too strange in this way that, right, this exactly this 2m minus k is what? This 2m minus k is something like this, you see, right? Wt roughly you can see is k, then this is, right, 2m minus k, all right? On the other hand, right, so how this is useful is this. Remember how I was going on and on about how this is super hard to derive? If you have something like this, right, then what you're having is the joint distribution of Brownian motion
and its own running max, right? I mean, the joint event, right? Joint event from which, of course, right? If these two events are true, then you can write probability are equal, right? Because if the two events are the same, the probability they're happening is the same, are the same, right? So this is like the joint event of prime motion and its own running max. So the moral A is that instead of looking at the distribution of the running max by itself, we look at the joint, right, between the prime motion and the running max. By the way, right, this is just better. This is not worse than this. Why? Because from the joint, you can always derive the marginal, right? So this is actually better. So this can imply this, all right, but not the other way around. Second of all, exactly, you see that this is something that we still don't know because this is hard, right? This is what we claim to be hard. On the other hand, this joint event collapse to a single event, if you will, based on BT. Now, if BT is a complicated thing that we don't know anything about, then this is no good. On the other hand, BT happens to be Brownian motion. Therefore, this is just a normal random variable. Therefore, we completely can control this probability. So therefore, right, the moral of the story, if we can show this, is the joint distribution of a prime motion and its running max collapse to the distribution of another prime motion. So that's the beauty of this reflection principle, right? So it allows you to control the distribution of the running max through a reflected, right, prime motion. Okay, so now why is this true, right? Is what we want to say next. Why are these two events? Why do these two events hold? Now, I want you to at least intuitively see that this is not far-fetched, right? Because in this picture, that's exactly what we're doing here, right? Notice that if you look at it superficially, you say it's believable. But if you study it, there's something a little bit subtle going on. So you want to understand completely. Notice that if K is not less than M, right, then this is not true. You need this. You need this, all right? And in this picture, right, roughly speaking, this is K, right? This is K, right? You're asking for WT less than or equal to K. And then this is roughly, right, 2M minus K right here. All right. So you see, right, again, right, because of reflection, right, if WT is less than K, BT is bigger than 2M minus K. But let's try, right, to work out this in a more rigorous explanation and point out the subtlety. So the reflection principle WT less than M, right? Sorry, see, WT less than K, MT bigger than M is equal to BT, right? Bigger than 2M minus K. This is true for K less than M. And let us remind ourselves, right, that BT is reflected by motion. In other words, it's WT if you are before the heating time, and you are reflected if you are after the heating time. So now, right, notice that somehow you have to tag along this guy, which seems strange, right? Because somehow WT seems to be related to WT only, right? But let us investigate. Now, to show two events are equal or equivalent, right, if you will, then you usually try to show the implication both ways, right? You try to show that, one is contained in the other, which is, implication. So let's show implication this way, right? Now, notice, right, the thing is, BT is here, right, in a way has two identities. It could be this or that, right? It could be WT or reflected WT, depending on where T is. Notice, right, again, this identity does not depend on whatever T is. This identity holds true for any time. All right, that's the key. This identity holds true for any time. So the tricky thing is, right, to identify which part of the identity that BT is taking on, right? And the hint for you is actually, it always takes on this second identity. It never takes on this first identity. And that's because of this, but we'll explain, all right? So exactly, right, to going forward, we want to go from left to right. Now, so the event that MT is bigger than M, right, what does that imply? MT, right, is the running max of the Brownian motion, right? If MT is bigger than M, what does that imply? You guys have mapped the running max before, right, in your homework. So you saw how the running max works. So if MT is bigger than M, what does that imply? Well, I guess the relevance here for us is just whether we are before or after this time, right? So if MT is bigger than M, are we on this right-hand side, right-hand panel, or left-hand panel? Which one? Yeah. Because? Right. Because if we're in the left-hand panel, MT cannot be bigger than M, right? Because in the left-hand panel exactly means what? That the Brownian motion never crosses M. Therefore, the max cannot be bigger than M, right? So MT bigger than M just means that tau T is bigger than tau. All right, that's all. MT bigger than M means we have crossed the time horizon, right? Sounds like a, you know, this event horizon in black hole, that kind of thing. So anyway, right, we have crossed that, okay, event horizon, and the Brownian motion has been reflected. All right, that's all it means. So right, but if that's true, then couple with WT bigger than K, that must imply BT is bigger than 2M minus K. All right. Any questions so far? So that's the easy direction, the reverse direction. In other words, we want to go back, right? Notice you have to be rigorous like this, right? If you only go forward and you don't prove the backward, then all you show is this is contained. And so these probabilities may not be equal, all right? It may be less than, for all you know. Okay, you have to be rigorous and show both ways. And usually one direction is harder than the other, right? And that's where all the money lies. So what do you think? How do we go back? So again, right, going back, notice that these two relations are kind of, you know, corresponding as long as you have something like this. But right, notice that going back, you have no clue, or at least the clue is not direct, right? Going back, you don't know, at least directly, where T lies. So how can you tell, right? Again, you see, the key is, so right, so let's take a look at the picture. So again, right, BT is bigger than 2M minus K. The important question for us is, are we on the left or on the right panel? And why? What do you think? Now, right, this is not that easy, and exactly why we want to work through this, right? And here's the clue, right? The clue is we haven't used all the hypotheses that we talked about in the reflection principle. Which hypothesis we did not use? Which hypothesis did we not use? The hypothesis K less than M. All right. Now let me say this, right? Let me say this so you appreciate it. If you just want to purely look for the joint distribution between K and M, between WT and M, right? Do you need to require that K less than M? If you just want to purely understand the joint between WT and MT, do you need to require K less than M? Again, right, there are a lot of small things in here that you is kind of tedious, but you want to clarify. For example, first of all, right, you guys have taken probability. I hope that's the reason why you admitted to this program. So, but if you are to draw, right, the joint density of WT and MT, right, what kind of region, what is the domain of this joint density? Can anyone tell me? You understand what I'm trying to say, right? When you look at the domain of the joint distribution of two random variables, what's the domain? Is it everything? By domain, right, I mean the support, the support of the pair of the random variable. Where, right, where they take non-zero density. You understand what I'm trying to say? For example, right, if I have like, join uniform 0 and 1, right? Then what's the domain of X and Y? The domain is the unit square, right? Because it doesn't matter how they are jointly distributed, they cannot escape 0, 1, right? Understand? But of course, right, that's just to give you an idea of what the joint domain is. And for example, if X, Y are joint normal, right? Let's say normal mu sigma, right? Like this for the multivariate bivariate normal, then the domain is the whole R2, right? Because the joint normal can go anywhere, right? R2. Now, what about WT and MT? What's their natural domain? Because we are looking at their joint density, right? So we need to know their joint domain. Where is it? First of all, can it be the whole real line? Sorry, the whole R2. Why not? Huh? What is positive? What part is positive? Both of them? Exactly. So very good. So MT itself is always positive. That's excellent. Why? Because it's a running max at the bar motion, right? And bar motion is 0 at 0. So MT can never drop below 0. Very good. So first of all, right, it should be this. It cannot be below 0. But is that it? So is it the whole positive y-axis? Is that it? No. What else? When you look at joint distribution, you have to pay attention to, is there any obvious relation between the two? Is there? What's the relation? Relation is, right, by definition, Therefore, you have to draw a line y equals to x, right? And the domain is everything above this. Agree? Right? Because WT can be negative, but MT can be positive, so the domain is over here. All right. So that's the domain for now, right? Now, look at the event that we're interested in, right? We're looking at the event MT bigger than M, right? WT less than K, right? So let's just pick an M and let's pick a K, right? And see what region we're looking at. So the region we're looking at will be MT bigger than M, right? So we're looking at this region. Agree? Now here, right, I guess I was instinctively drawing K less than M, right? I was instinctively choosing K less than M. But is there anything wrong with just the picture itself for me to slide K over here? Is there anything wrong for me to slide K all the way over here? As far as the event is concerned. Is this event okay? Is it sensible? Sure, right? It's just this weird shape. So it's no longer a corner shape, right? So because you have to be mindful of, right, how WT and M are interacting. Yes. But a priori, I have no concern whether M is less than K or M is bigger than K as far as I look at the joint probability. Does that make sense? Okay. Of course, right, again, if K less than M, the picture is much nicer. It's just the left corner. But if K is bigger than M, somehow you have to take that, right? In the corner basically drop below the line y equal to x. Therefore, you have to, right? But this kind of thought experiment or this analysis, right, tells you that this condition plays something else, right? It's not just about looking at a joint, right? At first you think, okay, because WT is less than M, somehow it's natural to choose K less than M. That's not true, right? There's no such logical requirement. So to recap, right? What do you think? How does that hypothesis enter into us deciding whether we are to a right or to a left of these events? Okay, let's just do simple deduction, right? If K is less than M, what does this imply? Right, that BT is bigger than M, right? Because K is less than M. Okay, so that implies that. Does that help? If BT is bigger than M, can we tell whether we're to the right or we're to the left of the panel? Why? Why is it that we must be to the right? Yes, you are, Shinan. Just push your. Yes. Why is it intuitive to you? Say it. Because if it were to the left, then what must happen?
It's always less than M.
Correct. And why is it always less than M? Why?
Because in the graph,
Uh-huh.
T is always equals to WT, and WT is always less than.
There you go. Exactly. Right. There you go. See, you know it, right? Just say what you intuitively think. By the way, I'm saying this because this might hurt you on interview, right? you can understand things. I have no doubt of that, but don't act like humble. I mean, I know that us Asians like to act humble, but that hurts on the interview, because they might think that you don't know stuff when you say that. I mean, I know that you know it, so try to express it as much as you can. It's not like you're talking bullshit, right? You don't. So okay, right? Try to bring that out. Okay, so very good, right? Exactly. That BT is bigger than M really means we have to be on the right hand side, because if on the left hand side, right, by definition, BT is WT, so it must be less than M to begin with. Got it? So that's exactly where we use K less than M. All right. So let's write that down. Right, and this is because M is bigger than K. And this implies that, right, T bigger than tau again, because, right, if not, then BT will be WT, and so BT must be less than M, right? All right. So, and then that's it, right? Because if T bigger than tau, then we establish that, right, that exactly that if we pass the event horizon, then the max must have crossed M, right? And because WT takes on this form, right, then WT must be less than 2M minus K, right? So let me write that down. So we passed the horizon. So we know that BT has been reflected. So that must mean that WT is less than K. All right, so we established that. Any question? Okay. So we're almost out of time, right? So we'll pick up on Wednesday. Sorry, Thursday. But let me tell you, right? So where do we go from here? So where we go from here is this, right? That we're almost there. We just have to clean up with technicality. First of all, notice, right, that exactly, right, because of K less than M as well, that, we have this kind of corner, right, inside the region rather than this kind of thing. So it allows you to derive the joint density. All right, you can derive the joint density of WT and MT by differentiate this with respect to M and K if you want. All right, you can derive the joint density of WT and MT, right, with respect to if you by working on this expression. However, right, knowing the joint density with this is still messy business, because, right, eventually we have to look at the probability and the expectation. Moreover, right, we still have this drift to look at if we are dealing with the, the Black-Scholes model. Okay, so we need to talk now. So now we need to be precise about what kind of change of probability that we're using, that kind of thing. So eventually what I'm trying to say is, right, in theory, we're done here, but the calculation still needs a lot to do. So eventually, right, so next lecture, we'll explain how the H function, right, H alpha, beta, whatever, SK, I forgot already, right, that enters, right, that MK, right, sub S. The H function exactly enters because we now take this structure and then, apply that to the pricing formula, right? And so that's the next step, okay? But the theory kind of is done here, right? The rest is just technical, like cleanup. But there's still something important to talk about there. All right, so that's all for today. All right, I'll see you on Thursday.
Thank you, Professor.
Thank you.